Okay, is that better?
You're still not full screen.
In that case, I have no idea what to do.
Try function F5, Pete. F5.
It's a Mac, that won't help me.
Right.
Yeah, just full screen. Just full screen on your PPT.
There we go.
Yeah, there.
Better?
Yep.
All right. Okay, sorry about that. Despite using this many times. All right, so as I said, what I'm going to do today is introduce you to the Midcontinent Rift, those of you who don't know it. I'm going to talk about some of the ore deposits on the rift, and then talk about some of the geochemistry and some of the ideas I have about what may or may not be right and wrong with rift models. I saw some names on the list of participants there who will have heard me given parts or all of this before. Apologies to them if they were hoping for something new and exciting. But for the rest of you, hopefully this will be an interesting, and I look forward to, as always, comments and discussions as we go through. All right, so for those of you who aren't familiar with the rift, we're sort of sitting right in the middle of the North American continent. It's a 1.1 billion year old event. Sorry. Here. All right, so 1.1 billion year old event, widely accepted to be a large igneous province, so caused by a mantle plume with mafic and ultramafic intrusive rocks associated with it. And some of those rocks host nickel copper PGE deposits. It's one of the biggest rifts, it's one of the biggest lips that we recognize. It's also got some of the least known mineralization. There are deposits around, there are some good exploration targets, but to date, the only mine in the rift is a relatively small operation called Eagle. The image on the left there is sort of showing the geophysical extent of the rift in that red blob, and then sort of the estimated suggestion for the plume head, which is that sort of circular area.
Hi.
Okay, so looking at the
Sure, no problem.
here, just to give you an idea of the scale and extent of this, we're looking at two images, a narrow mag image on the left and a gravity anomaly map on the right. And you can see the expressions extends all the way down from Lake Superior down to sort of Minnesota, Iowa, and further south. The best exposure of these rocks, though, is up around Lake Superior. The further away from the rift or from the lake you go, the harder it becomes to actually see anything. And if we look at a geological map here, you can sort of get a rough sense of what we're looking at. North of Lake Superior, we have the Osler volcanic group. The Osler volcanic group in here, there's sort of, pale group here, volcanic sequences. There's the North Shore volcanic group running down through the states, this large Duluth complex intrusive rocks, and then a series of sills, the Logan sills and the Nipigon sills up around Thunder Bay. I'm sort of sitting in around here somewhere in Thunder Bay right now. How do we know about the rift as well as we do? Well, there's been quite a bit of research, and then back 20, 30 years ago now, there was a number of seismic lines run across Lake Superior back in 85, 86, both for exploration, and then GLIMPS was a public data collection project. You can see that sort of red line there is the GLIMPS survey, and we're going to look at the results of that now, and just to give you an example of some of the stratigraphy. So this is the interpretation of that GLIMPS line. There are some groups right now trying to reinterpret this data and get hold of the data, but you can see the key thing is that we're looking at probably 30 kilometers of mafic volcanic rock flooring the bottom of Lake Superior. As we get out to the edges of the rift, those sequences thin, but there's evidence for a major continental rifting event and large volumes of igneous rock intruded into that sequence. Sort of the current model, the generally accepted model, is that around 11, 12 million years ago, maybe 11, 20, a mantle plume impacted against the base of North America. that caused the main rift magmatism events that we sort of see and are expressed in the volcanic and intrusive rocks. Volcanism sort of shut down probably about 1080, 1086, somewhere in there. And at that point, we sort of started getting some sediment infilling in the top of this basement. And then around 1,000 to 900 million years ago, we get some compression and we get some faulting. And since then, pretty much nothing has happened to the rift geologically. So these rocks are remarkably fresh, remarkably unmetamorphosed. If you look at some of the volcanic sequences, there's zeolite metamorphism, that's about it. The textures, the physical mineralogy, we're doing some melt inclusion work right now, and these are some of the most pristine melt inclusions we've seen that are 1 billion years old. So these are really well-preserved rocks and give us great opportunities to do a little bit of research and try and understand what's going on. In terms of mineral deposits, we've got quite a wide variety of mineral deposits around the rift. There's some nickel, copper, PGE sulfides. So Eagle sort of sits down here, the active mine. Some of the ones we've worked with, talk about up around by Thunder Bay, are sitting up through here. There's also these copper nickel PGE systems. So these are the Duluth complex for the most part. Often, in case of the Duluth complex, very high tonnage, but very low grade. We also have some titanium oxide systems, again, associated with the layered intrusions of the Duluth complex. We have some copper deposits, silver islets, which sits just around, copper deposits out on the islands out there and down here on the north shore or south shore of the lake, which have been mined for 15 or 10,000 years by the indigenous populations. There are some beautiful metal tools that can be found archaeologically. So there's a long history of the copper mining. Copper sulfide systems, there are some SED-hosted copper systems in through there. We do have Silver Islet, which is the silver mine, which back in the day it was being mined. In the 1800s was the largest silver mine in the world. So there's a long history of mineralization in the region. The main exploration targets at the moment, though, are the nickel copper PGE systems. All right, so I mentioned some of the low-grade deposits. We're not going to talk about those a lot today. They're mainly hosted within the Duluth complex, as you can see here, and there's a series of them, North Met, Masaba, Nokomis, all running in through sort of the margins of the Duluth complex. And if we look at them in terms of their grade and their tonnage, they are very high tonnage deposits. They're some of the largest tonnage systems out there, but the grades are also very low. So that makes them economically quite difficult to mine. There are permitting ongoing at the moment. I think it's North Met, the Polymet deposit, are still in the process of getting their permit. They've had a few hurdles as the US government has changed, but they're moving forward. They'll probably be the first mine to come into production, and we'll see where these things go. There are certainly potential for a lot of metal if they can get through some of the permitting and geometallurgical challenges that they're facing. What we're going to talk a little bit more about today, though, is the high-grade stuff. This map's a little deceptive. It's a little old as well. So Lac des Îles up here, Lac des Îles is a palladium mine. It's actually an Archean deposit, so it's not part of the Midcontinent Rift. We have resources out at Marathon, Eagle, which is now actively being mined. And then there's Tamarack, which is another Rio Tinto project. And then we're going to come up and talk about Thunder Bay North. Used to be explored actively by a company called Panoramic and in part by Rio Tinto. It's currently now held by a company called Clean Air Metals, who are again advancing the system and trying to, hopefully in the next few years, bring the deposits into production. The high-grade deposits, these nickel copper PGE systems, are all associated generally with these ultramafic intrusions, and these ultramafic intrusions marked by the red stars for the most part, seem to be dated quite early in rift history. So 11, 15, 11, 12 million years ago, very early in the magmatism of the rift. And that's where we seem to see these. So Eagles down here, we're going to talk about Currant Lake, Seagull Disraeli. I saw Jeff Heggie on here. Jeff did his thesis on Seagull. There's a bunch of these things out here. None of them have been, to this point, they've got the grade and the tonnage to make a deposit, but there's a lot of exploration going on. Current Lake has a pretty good hope, I think, and then there's a new one, Sunday Lake, which is not shown here on here, which is currently Impala, Canada are looking at, and again, that's a good hope. I think there's some good mineralization in these ultramafic intrusions. So what are some of the characteristics of these ultramafic intrusions when we look at them? Well, like I said, they're all early, 1107, 1105. Thunder Bay North, the age on here is 1120 plus or minus 23. There is a little more newer age that we're hoping to see released fairly soon, which I think will bring it down to around the 1107, 1105 range. But some of the common features of these things, if you look at these descriptions, is there's this mix of ultramafic and mafic rocks, but they're often described as fin-shaped intrusion or tadpole-shaped intrusions or sinuous tubes. And the commonality that we're seeing with these is these units are actually what we're calling chonoliths, and they seem to be feeder units to other intrusions which may or may not have been preserved. They're often sub-horizontal to horizontal. They're sinuous, and they're quite small in many cases, which can make them challenging exploration targets. We're going to focus on Thunder Bay North. It's got a neat little exploration history for those of you who don't know the deposit. And it's also got this sort of quite well defined, as they've done a large amount of drilling as through panoramic until quite recently. Platinum and copper rich, disseminated polymetallic sulfides, fairly sort of almost 1-to-1 platinum palladium ratio. Again, the reserves at the time I put this together, which was a few years ago, was 9.8 million tons at 2.3 grams platinum equivalent. So a fairly good size system. The discovery story is quite interesting. A guy called Graham Wilson was involved in the discovery, and initially it was looking at boulders. They first found some boulders on the west shore, which they, in 2001, which had some very good assay values, 9.5 grams per ton platinum palladium. They followed that up, doing some detailed glaciology and figured where the ice flows went, and found some more boulders on the north shore. Again, similar sort of grades. And then their first hole, 001, was their discovery hole, intersecting 10.5 meters at 2.8 grams per ton. So it's a neat story in terms of sort of grassroots exploration, you know, boots on the ground, and they got very lucky and they hit mineralization with their first hole. We take a look at what some of the mineralized boulders look like. You can sort of see some examples here of the features we're looking at. They have often what's called this elephant skin or onions or wrinkly texture, which is very typical of these ultramafic boulders, very rich in sulfides on a cut surface. And this bottom up photograph down here is just showing the drilling. Here's the lake that they were finding the boulders on the shore, but the first drill hole on the shore of the lake drilled that way, I think, into the lake, and they hit mineralization in the first try. The whole area we now know a little bit more about as a result of extensive drilling, extensive geophysics that's been flown through the region. And we do get this idea that we're looking at these conduits, these chonoliths, these feeder dikes. One common thing is that we're close to is this unit here, the Quetico Fault. This is a major sub-province boundary in the Archean sub-provinces, so a lithoscale fault unit. We've also got this feature here, the Escape Lake Fault, which is a splay off that Quetico Fault. And you can see that there seems to be a link between the magmatism in terms of proximity to the main fault, and possibly some sort of geometric control related to this Escape Lake Fault over here. This is Current Lake. We can see the extensive sort of mineralization they've picked out through here. There's ongoing exploration in Steep Ledge. This area here, which Rio drilled, had some very good grades and tonnage. And now this whole area has been consolidated by Clean Air Metals, who are taking it forward and working with us here at Lakehead and Derek Wilton at Memorial, trying to figure out the magma fluid flow, the directional systems, and how these systems work, and where the really good, juicy, high-grade mineralization is. But from an exploration point of view, these are relatively small targets. So finding them with big regional geophysical surveys can be challenging. So we're always looking at other tools that we can apply to help us understand them. Just a couple of mineralization photographs here. Some of the sort of typical things we see with disseminated sulfides. the range of platinum group minerals we get, you can see we get some massive sulfides with up to 60 to 100 grams per ton platinum, palladium, 8 to 15% copper. So there are some really, really high grade zones, and then some more typical of the disseminated sulfides that we see throughout. Other examples that we get sort of some sulfide veins in there, often in these bridge zones where the bonanza grades maybe up to 10 or 20 grams per ton platinum and palladium associated with these things. Obviously they're hard to track, hard to predict, but they're out there. So there are some aspects of the mineralization which lead to these very high grades. There's some really interesting work that the guys have done through their drilling, Magma Metals and then Panoramic when they were there, and Jeff Heggie, who was involved in a lot of this work, will I'm sure correct me when I get all this wrong. But as we change the lithologies through which the rock or the conduit, the chonolith passes through, the geometry of the body changes. So when it's predominantly going through the granitic sort of rocks at the basement, we get these more tube-like. And then when it's sort of constrained into the quetico sediments, these brown units, they're often more sill-like, I guess, in their appearance. They take on a very different orientation, a different shape. So there is a strong lithological control, I think, on how these things form. But there's also this control of these faults. And when we look at the ultramafic intrusions, these early ultramafic intrusions throughout the rift, they're often occurring around major lithospheric scale structures. So it does seem to be a link in possibly allowing these magmas to move up some of these crustal conduits early in the rift history. So this is sort of their model they've put together of what the whole body looks like. Sort of, again, changing in shape from narrow conduits to wide conduits, and changing in shape from sort of quite broader horizontal pipes to quite narrow pipes as you move along the sequence. They put together an exploration model. This was again a few years old. I think it probably still stands. They'd argue that it's flowing, I think, from south to north, the magma. So it's coming in at the southern end and flowing northwards from this wider zone into this narrow zone. Multiple sulfide traps possibly existing in different places throughout the system. I think the key thing with all these chonoliths, whereas places like the Duluth complex, we think they are just sort of layered intrusions, you know, relatively simple like Skaregard and things like that. Here we're talking about conduits. They're pathways for the magma. So the magma is flowing through these chambers on its way to somewhere else. So they're a little different, I think, in that respect to some of the other nickel copper PG systems we think about. All right, so that's a little introduction to some of the mineralization. What I want to talk to you now about is some of the work we've been doing in trying to understand the geochemistry of how we piece these sequences together. And when I moved to Thunder Bay 20 years ago and got involved with the research, this sort of map was more or less what we knew. Especially north of the border, there were these Osler volcanic groups, and then there were these orange groups, which are mainly sills with some dikes, all dated. So they were all called the Logan sills. Everything in orange was called one unit. We had one composite age taken from some material here and some material up here, and they mixed it all together and dated it and come up with an age of 1109. It's actually a pretty good age, it turns out, but the methodology was a little bit suspect. What's different, I guess, is that in the north of the area, and I'm going to focus on the area in the Canadian side of the border, on the northern side, we see mainly sills and ultramafic intrusions. So up here around Lake Nipigon, there's very little in the way of dikes being recognized today. Whereas down south of Thunder Bay, down here, we see a lot more dikes. We still see sills. We still see some ultramafic intrusions, but they're less common. So most of the ultramafic intrusions are up in this sort of area north of the city of Thunder Bay. We have a fairly extensive data set now. We have more than 2,400 whole rock analyses. We have about 800 platinum group elements, 100 isotope data, radiogenic isotopes. We've got a pretty good data set that we've collected over the last 15 years, 20 years through a bunch of graduate student projects, working with the OGS, All this data is pretty much out now in Ontario Geological Survey miscellaneous data release files. I think there's a new one either just come out or coming out soon with the latest compilation. So all this data is out there. If you want to take it and play with it and tell us we're completely wrong, I'm fine with you doing that. It's a very nice database to work with. My interest got involved back with what we call the LNRGI, the Lake Nipigon Regional Geoscience Initiative, back in about 2007. And the goal there was the Ontario government put some money up to try and better understand the mineralization potential of the area around Lake Nipigon. We did a whole bunch of geochronology, some of the first sort of detailed geochronology on the rift. Larry Heeman did this. We published it in a special issue of Canadian Journal of Earth Sciences back in 2007. And again, you can sort of see a lot of these ages are coming in quite old, 1117, 1109, 1112, and that's sort of those older intrusions, those older dike phases that are in there. We also did a bunch of geochemistry, and that's where it got interesting, because we came to realize quite quickly that this sort of homogeneous orange unit, this sill unit, which had been mapped as a single thing, actually contained at least 5 different geochemical units. There was the jackfish down through here, inspiration up through here. Oh, this is jackfish and this is shillaber, I don't remember. There's a number of different types of magmatic unit that we were able to recognize, suggesting that it was a much more complex environment than we previously realized. So we developed a couple of geochemical diagrams that helped us break things out really well. Lanthanum samarium versus gadolinium ytterbium, you can see here. And generally the ultramafic units, so Hele, Israeli intrusions, are plotting at these higher gadolinium ytterbium ratios, whereas things like the Nipigon sill complexes are plotting down at these lower values. And when we looked at titanium versus magnesium number, we could sort of see 2 distinct suites, again with the ultramafic units plotting into this sort of field further to the right. So we were able to use these discrimination diagrams to help us try and classify and break things out across the rift. And you could sort of lump things together, that we had the sort of the Logan sills and Nipigon sills, inspiration sills, out as these separate units, and then try and help from there piece together the history of the rift. We tried the same thing down the south, so we've carried across our fields, and then we started playing with the units down to the south, and the Logan sills are sitting in here. We found a brand new ultramafic sill, Riverdale sill. Our discovery outcrop was behind the Robin's Donut coffee shop. Coincidence, we were just stopping there and, happened to find a new unit, worked out well. But there's a whole variety of different, now we recognize distinct units throughout the rift. There's quite a few dike systems throughout the rift. We particularly see them down in the south. If you look at sort of the main thing, there's, broadly speaking, this northeast trending unit, which is the Pigeon River dikes, the Cloud River dikes, which are these northwest ones, and then Mount Molly, which runs through here. Until quite recently, the ages of these have been a little controversial, particularly the Pigeon River. We've had some 1140 and 1080 ages come back from these. Walter Bleeker from the Geological Survey of Canada has been doing a really detailed redating of a lot of the more unusual ages that we found in here, and they're all now coming into a much more consistent grouping. We're seeing a lot of those really spurious older and younger ages going away, and it looks like this dike swarm, or these dike suites, are more or less the same age. The chemistry of those dikes is a little interesting. The Pigeon River dikes, which are plotting down here, are geochemically similar to the Nipigon sills. So if you remember, the Nipigon sills are those ones far to the north. They're not similar to the Logan sills, which is the ones they intrude into. So they're not acting as the feeder dikes to the Logan sills. And we've only, in all our work down there, we found 1 dike with Logan sill geochemistry, and that's a single dike about 0.5 meter wide. So there's some challenges still, I think, in trying to understand the feeder systems to all these things. Where did these Pigeon River dikes that we find in the south, what were they feeding? What magmatic units were they feeding? Was it the Osler volcanics? Were they feeding something else which has since been eroded? There's a lot of work we're still trying to piece together, trying to understand these systems. There's a few odd units as well sitting in through here. The Sibley dikes are an unusual sequence of dikes on the Sibley Peninsula. Provincial parks are a little challenging to sample, but they're plotting up in these ultramafic units. So we've speculated that maybe they are feeders to some of those ultramafic sills that we see, and are perhaps are interesting from that point of view, because we don't see a lot of the more ultramafic compositions floating around. There's a lot of physical evidence in both the dikes and the sills for assimilation. So these magmas have had a very complex history, and that can make it quite challenging for us to understand where they originally formed in the Earth's interior and what they're telling us. And there's some really good photographs here. We've got sort of a clot of partially assimilated material. This is a partially assimilated material from the Sibley, which is a 1400 million year old sort of red bed sequence that sits very close to the surface, could only have been assimilated at shallow depths, and then these quite complex assimilation textures we see in these other two dike photographs here. We also see evidence for this in the geochemistry. So this is one of these Jarvis Point down through here, where it's cut by a Pigeon River dike, and we took 4 samples from that dike. I think Richard was involved with this sampling years ago, Richard Ernst. And what's interesting is that as you move closer to the edge of the dike, so sample 3, which is this black circle unit up through here, shows a very different geochemistry with this strong thorium enrichment, pronounced negative niobium anomaly, which is consistent with it having assimilated continental crust. So we know that these dikes and these sills are assimilating material as they are in place, but there's also isotopic and geochemical evidence that they're also assimilating material at depth in some upper or possibly lower crustal magma chambers. So it's a complex, different feature in there. And we can see some of these geochemical patterns in through there in terms of their chemistry. The ultramafic sills, this is Shillabir and Disraeli, but it's also true of Seagull, generally don't show those strong contamination signatures that we see in some of these other units with this light rare earth enrichment, these negative niobium anomalies, which are consistent with them having assimilated older continental crust, which at some point in its life went through a subduction zone. The ultramafic rocks don't. They look a lot more like ocean island basalts, things that we would associate with mantle plumes. So again, we're seeing different signatures, and if we want to unravel these and try and understand what's going on within the rift, we need to start playing with that data to sort of piece it all together. So this is some of the radiogenic isotope data we have, neodymium versus strontium, sort of primitive mantle around this time, or would be sort of sitting up here. So we have a few samples which are relatively primitive and uncontaminated, but everything else seems to have undergone some degree of contamination, variable amounts depending where we're at and what the signature is. But you can sort of see some of it's pulling down very steeply on the neodymium data to these -6 values. We think that's probably picking up basement Quetico, which at the time of emplacement would have been about -15, -20. Other stuff seems to be pushing out towards these high strontium values. The Sibley group, those sediments I talked about, that 1400 million year old sediments plots out there. So we think there's probably a mix of deeper contamination in the lower chamber and shallower contamination up through there. Steve Shirey and Sue Nicholson years ago, or Suzanne Nicholson, have argued for sort of the involvement of subcontinental lithospheric mantle and processes like that. And we're certainly seeing, I think, evidence for these different types of contamination, different contamination processes through there. All right, so that's a sort of a really quick introduction to the geochemistry. It's a quick introduction to the mineralization. I want to sort of try and round this out by reviewing some of the existing model for the rift, and getting you to think about why this may or may not be true. So if we look at sort of the typical definition of a rift, and this is Richard Ernst and Buchan a few years ago now, they recognized at that time that there were 31 sort of mafic magmatic events in the geological record that could be definitively, or at least confidently, associated with upwelling mantle plumes like the thing we see under Hawaii. They suggested there are a number of characteristics of these. They have a large aerial extent, greater than 100,000 kilometers squared, relatively short emplacement time, often or nearly always associated with a giant radiating dike swarm, sometimes a link to present-day hotspots. And then they suggested that if we look at the geochemistry or just look at the dike swarms, maybe there's as many as nearly 200 of these systems. This is the model for the Midcontinent rift as we stand. We have this is Jim Miller's model, this early magmatic stage at 1109. That's where we're getting some of those early ultramafic intrusions. A late magmatic stage, or the main magmatic stage, latent magmatic stage in 1107. A lot more magmatism in there, a lot more sort of impact of the plume, more melting at the base of this continental crustal unit. A sort of a stage, the main magmatic stage in there, and then the late magmatic stage. So there are multiple pulses. With the geochronology we had at the time, this sort of worked, and with our understanding of the geochemistry. I think, and I'm going to try and convince you, I think there are some challenges to this model that we need to address. There's a bunch of people playing with these ideas at the moment, and I think we'll see some stuff come out. So what I see as the main issues with the Midcontinent rift representing a simple, large igneous province like Norilsk or like some of the other typical examples we see are the geochronology, dikes, the paleomag, the nature of the ultramafic rocks, and some of those, there are some weirdnesses happening around this time. So I think we need to peer through the mist, peer through the fog, and try and figure that out. If we look at the geochronology, this is Larry Heeman's compilation from 2007. And we have this early event, which includes this Abitibi event. The Pigeon River Dike I probably wouldn't put there anymore, but it's 1140, 1150 event going on, then there's a gap. And then we start sort of seeing these 1120 age events coming in through here, which maybe you break up into these stages 1, 2, 3, and 4. The mineralization, those nickel copper PGE mineralized intrusions, as far as we know, are all sitting up at this point in time up in here. I mentioned Richard Ernst has been playing with the geochronology or redating a bunch of these units. And I apologize for the size of the writing on this, but this is Wouter Bleeker's, so Wouter Bleeker, not Richard Ernst, Wouter Bleeker's diagram of his current ages. There's a whole bunch of new ages in here, suggesting where these things come and go. Some of it still works. Some of it I think holds up in terms of timing. There does maybe seem to be different phases in through there, but certainly I think some of the really odd outliers that were suggesting sort of 60, 65 million years of magmatism probably don't hold up. But we do still have some quite old ages down from sort of 1140 sitting in through here, which he hasn't yet managed to make go away, all the way up to about 1080. So even if we take sort of the conservative area in through here at about 1120, we've still got 40 million years of magmatism. And that's not consistent with what we see for Piranha Etendeca or the Deccan traps, where the vast majority of the magmatism seems to come in 1 or 2 million years. There's something different about the rift in terms of the longevity. Paleomagnetism can also help us try and understand that. This is Henry Halls a few years ago coming out and sampling some of these suites and taking geochronology on them, or so paleomag on them. And this is the map from years ago from Pesson and the Halls and all that sort of data back there. And what's interesting is that within the Pigeon River dikes, we're seeing both normal and reverse dikes. Now, there's a campaign going on at the moment, if we're ever allowed back in the field, and COVID goes away, to come back and try and resolve some of these apparent anomalies. But it does seem at least that there is protracted paleomagnetic signature preserved within that rift sequence. What's perhaps more interesting is some of Nick Swanson-Heisel's work. Nick has been doing really detailed paleomag combined with geochronology and a bunch of the volcanic sequences around the rift. And this is the Mainz Point sequence here, which is sort of down at the southeast end of the lake near Sault Ste. Marie. And he's done a really detailed paleomag study in through here. And what he suggested based on that and his geochronology is that the plate motion rates were about 20 to 40 centimeters per year. The only other time we sort of get that theoretical limit being approached was when India was moving north before it slammed into Asia to give us the Himalayas. That's a really rapid rate of plate movement. I struggle with how you would have that rapid rate of plate movement and maintain North America above a plume head for sort of 40 million years. There's different arguments. Some people have suggested maybe the plume head becomes detached, or there's different arguments. But to me, it's a challenging model to tie in those high rates of plate motion with the idea of a continent above a more or less static plume head. Radiating dike swarms. This is some of the best evidence we have for ancient large igneous provinces. A couple examples here from the Metallogeny swarm and the Mackenzie swarm. And the idea being that you get these dike swarms, which are maybe up to 1,000 kilometers long, and you plot back their center points and they fix on a single point, and you can suggest that's the pierce point for the original sort of mantle plume coming up. If we look at the area around the Midcontinent rift up through here, notice that all the dikes seem to be rift parallel. This is the Barraga swarm down here, the Pucker swarm over here, all the stuff in through here. These dikes seem to be predominantly rift parallel. There's a few dikes floating around. There's some of those early Abitibi dikes, which do maybe appear to be radial, but there's no evidence of a mid-continent rift age radiating dike swarm focused on the rift. So that again to me suggests there's something different about this sequence. And we can look at that. If we blow up this little area here, we can see these dikes are all rift parallel. Just before I was putting this talk together, Richard reminded me of one of his papers from 2019, where they sort of make the idea of these circumferential dike swarms. And they've suggested in their 2019 paper that the dike swarms around the north shore of Lake Superior sort of fit with the idea of a circumferential dike swarm around what they term the Goodman swell. If you read the paper closely and look at the figure caption, they note that all the rift parallel dikes down through here don't fit this model. So I'm sure Richard will, get into me with this a bit later on. But if the fact that half the dikes we know about don't fit the model, I'm not convinced that it's perhaps the perfect model to explain this. And thinking about them being rift parallel seems to make more sense to me. The ultramafic intrusions. There's a bunch of them. A lot of people have argued that those early ultramafic intrusions require or suggest that we must have plume-related magmatism. In some of my early papers, I've made that argument as well. If you look at sort of the definitions, and this is the Campbell and Griffiths definition, they suggest that you want a magnesium content of around 14 weight%. A lot of the ultramafic intrusions are cumulates. So if we go back and take the olivine compositions, the forsterite olivine compositions, back calculate from that for a whole bunch of them, and they're all coming in this sort of forsterite 85, 82, 88 in there. You do the calculations, you back count them. Jeff Heggie was involved with this and Seagull stuff. You end up with 8 to 10 weight% for the original parental magma. So yeah, there are ultramafic intrusions, and they're interesting from a mineralization point of view, but they're perhaps not telling you about there being ultramafic magmas in these parental magmas. This is some of the work that Rob Kandari did for his master's thesis, and it is writing up at the moment. And just looking at the geochemistry, plotting it out on one of these sort of classic sort of mantle field, mantle source diagrams, what it seems to be telling us is that there is both trending towards contamination, but there also seems to be a trend from more enriched material to more depleted source material over the evolution of the rift. And again, I struggle a little bit with that being related to a mantle plume, where you might expect perhaps the plume composition to remain more constant. Perhaps if you had a waning plume, that might explain it, or perhaps as we need to think about some sort of different types of models in there. All right, so there's our original idea of what made a lip. How did we do? Well, we got a few things right. It's big. It takes a long time though. There's no radiating swarm that I can really see in the dikes there. Obviously, we don't have a present day hotspot. It's a billion-year-old. Geochemistry is plume-like for sure, but there's not really that radial or lineal dike swarm. I don't think. Others may disagree. So what else could be going on at that time that helps us try and understand what was going on? Well, we know for, again, some of the work that Richard Ernst has been doing, and some of it's been around for a while, there's a lot of other events around the same time which show similar geochemistry now. Angola, the Amazonian event, this Kalahari event we've known around for a while, 1112 to 1106. And then down in Arizona, there are dikes which are a little bit younger, 1080, 1090, again, suggesting that perhaps there was something going on globally at this time that could help us understand what was going on. The Stein couple have been recently working in this region and rift, looking at some of the seismic data that's been produced as part of the US array that's been marching across North America. And they've suggested that a different model is that it's sort of related to large-scale continental rifting away from Lake Superior. So the suggestion is that the rifting of Amazonia down through here and Laurentia from sort of moving away from North America somehow triggered this far field sort of rifting thing. I struggle a little with how this model works. It's not something I'm really convinced fits the data we have, but it's a model that's out there. Bright, who did the work down in the Southwest US and found the units down in Arizona, sort of suggested that perhaps the plume had come up and bifurcated. So it went down to the Southwest and generated a whole bunch of stuff, and then up towards Thunder Bay and Lake Superior to generate the Keweenaw lip. I guess this is possible. I don't know that we have good geophysical evidence for modern plumes doing that, but perhaps if it's coming up or under a continental crust and looking for zones of weakness to break through, then maybe that could explain at least those two units. And there's also this idea of super plumes. So Condi back in 2001 suggested that we have periods of time when there are regionally plumes clustered regionally within an area where the mantle becomes turbulent. You get multiple plumes coming up. The modern example is maybe this Pacific super swell or something like that. And there you get smaller plumes punching through, and maybe that's what happens for the Midcontinent rift. It's pretty hard to test that one way or another. Perhaps it helps explain some of the longer time frames that we see for the Midcontinent rift. But I'm not sure if it's really the right model to work on. The model I've been leaning towards these days is the idea that perhaps we're not looking at an active rift where a mantle plume comes up, causes doming, pushes apart the crust, but in fact we're looking at some kind of passive rifting event where the crust is pulled apart on its own and then mantle material wells up into it. That could explain the rift parallel nature of the dikes. We're not having a plume giving us that doming and that radiating swarm. Why then do we have the geochemistry that we do have in through there, that plume-like geochemistry? Well, there's evidence for a number of older dike swarms in through here, the Marathon swarm, the Fort Francis swarm, which are sort of older. Perhaps they left residues of plume-like mantle underneath the cratonic landmass. And then when you rift the continent apart, that goes under, ascends and causes melting. It's difficult to test that one way or another geochemically. At least I haven't figured out a good way of doing it yet. If anyone has ideas, I'd be really willing to talk about that. But that's one possible thing to try and understand. I think that we need to start thinking about other ideas for how the rift may have formed. This is my partner in crime, Mark Smick. We've done a lot of this work together in the rift. Just to sort of summarize up, that one of the things is that I had changed this from major deposit, has not yielded a major mine. There's no Norilsk-like thing. One possibility is because it's a passive rather than an active rift. I don't know if that would really affect things. Maybe there'd be less heat, less mantle dynamism in there, and that's why we're not getting these giant Norilsk-like deposits. It may also explain perhaps why we're seeing our mineralization close to the rift rather than distal. All right, I'm going to leave it there. That's sort of where I think we need to start thinking about the rift, the implications that has for mineralization. I'd be really happy to try and answer some questions. I see there's a couple of things coming to the chat there. So I will stop sharing my screen at this point and open the floor up to people to tell me just how wrong I am. Thank you very much.
Thanks a lot, Pete. Very much appreciate, very clear. And yes, we do already have some people in the chat voicing their the various types of questions that you're going to get. And obviously you baited some people out there, including, of course, Richard, who was one of our earlier speakers on here. So our first question is from Steve Cantor. And Steve, just unmute yourself and go ahead.
Oh, this is actually Sam. Yeah. Yeah, I had my email up there. Yeah, I just wanted to know that diagram you had with the chronolith geometry, and you were mentioning the lithologic control. Is there a depth component to that, or do you see that lithologic control at multiple depths?
That's a really good question. So if the model for the current lake and through there's not the depth variation is a couple of 100 meters from one end to the other, and Jeff Heggie was on here, he'll correct me if I'm wrong. So I would say no, in that case it's pretty much, there's such a limited range of depth that it's going to be a lithological control,
Okay,
rather than a depth control.
Cool, thanks.
So I see someone asked a question about the intrusive age versus crustalline simulation relationship. So the ultramafic units, which are the earliest units, seem to be the least crustally contaminated. But we don't have good enough age constraints on the sill units to really resolve that, I think, in terms of being able to break that apart.
Yeah, okay. We have Richard. Richard, just if I skip over somebody by accident, just chime in. But I think Richard is next.
Hey, Pete, thanks. That was good. That was a neat overview. If the passive margin idea, then does each of the pulses that you see in the age spectrum represent a pulse of extension? Is that your view on this?
Is that my view on that? I think probably, yeah. I think there's probably got to be that link, right? So there's always been that argument that we have that period of felsic magmatism that we see in the rift, the latent phase, I think Jim calls it, where the argument goes that for whatever reason the rift stopped expanding and the magmas pondered at the base of the crust, fractionated, giving us the anorthosite complexes, the felsic magmatism that we see in there. And I think that argument could apply equally well to a passive argument where you just, as you pull it apart, you'll see multiple pulses of magma. Even with Wouter's refined age states that he's doing, where we're getting better and better errors, we're still seeing a lot of overlap between these ages. We don't have those sort of really refined ages to sort of help us break out the magmatism as well as perhaps we would like. But I think, yeah, I think if you want to believe a passive argument, and there are arguments many arguments against a passive rift, I think the pulse idea would work. I think there is also a structural control though. We see those early ultramafic intrusions are coming along pre-existing lithospheric weaknesses. So I think it may be that some of that early magmatism is associated with that. And if you want to think about the 1140 stuff as being rift related, and not everyone does, then again, I think they seem to be associated with lithospheric failing.
With respect to the 1140, the Abitibi-Dyke storm, it's recent years. It was Kevin Chamberlain and others dating the Corson gabbros over on the Dakota side, and also at 1150. So there's a lot of, now on both sides of the Midcontinent, there's 1140, 1150 magmatism. So it does seem like that is a regional significant pulse. I know I saw it on Wouter's diagram as well.
Yeah, it's on there. I guess it's just there does seem to be a break in magmatism of, now we think probably 20 years before stuff that most of us would be comfortable calling truly rift related. So whether it represents an early event or whether it represents a completely unrelated something zipping along underneath the continent, yeah, that's a tough one. I'm ambivalent about where I fit that 1140 stuff into the story.
Yeah, well, potentially. Let me just ask one other question. Potentially, that would be a kind of a potential plume stage though as well, and then all the subsequent could be rift pulses. But one question was about I remember Siegel, I think, there was some talk about 1120, 1130 age at some point. There were some real older ages in the Nipigon plate through that 2007.
Yeah, so
what's the status of those ages?
so we haven't redated Seagull, but when Wouter looks at those, he doesn't like the choice of zircons for those older ages. And this is where I sort of throw my hands up with geochronologists in that it's, well, I don't like those zircons, so I'm not going to include them, and that makes the age this, right? So there's an element of that in there. I should check Wouter's not online before I start too much. But I think generally where we've got good ages like Current Lake and some of the other older ages that we reported back in that 2007 paper have been redated and have gone away. So I think I'm now comfortable with there being 1112 to 1115 ages. I'm probably less comfortable pushing stuff back much further than that. And it used to be that all the old ages were in Canada and the young ages in the US, which got people nervous, but there's an 1120 age for Eagle, a Dike-near Eagle, which is being reported. So we're seeing ages on either side now of that older phase. But yeah, 1115, 11, Eva Keto still stands, and that's 1117, 1118. That one hasn't been changed yet. So there is an older phase, but it's perhaps not as common.
Okay, great. Thanks, Richard and Pete, for that. I think Phil had a question. Go ahead, Phil.
Muting here. There we go. Sorry about that. Great talk, Pete. Nice overview and very much appreciated. My question basically is looking at the wider context for the MCR from that 1200-ish period for Abitibi at 1140 through the MCR rifting. Looking at the wider context, ignoring Amazonia and what the interactions might be, the Laurentian southeast margin leading up into that time in the Mesoproterozoic was an active margin. It was kind of almost like a Cordilleran style margin. So is the MCR possibly a response to some sort of margin parallel motions, and the pulses that we see might be sort of an interior response inboard of the margin?
Yeah, so that's a really interesting question, and it's something I don't think we're thinking enough about in how we tie these things in. I've been chatting with Mike Easton, who's my local Grenville expert on that sort of side of things and how that might fit. It gets tough to really resolve stuff well. I always used to struggle with the idea of really distal expressions of subduction until I started looking at some of the middle lower Yangtze stuff in China, which is 140 million years old in age and is 1,000 kilometers away from where the rift or the continental margin would have been, but shows a lot of back archy type signatures to it, or in terms of that. So potentially, yeah, it could be. I think the volume of magmatism that we see in the Midcontinent rift is not typical of, I think, what you might expect from a sort of far field expression of one of the, it's a possible idea, but I don't know if we really know. Yeah. Sorry, don't have a better answer than maybe, kind of, sort of.
Well, just a quick follow-up. One of the things that's been proposed for this Mesoproterozoic active margin for Southeast Laurentia is that it's fairly long-term, over a couple 100 million years.
Yeah.
And it got pretty hot. So those might be pre-existing conditions just to lead to the actual Cordilleran style margin itself that may drive something that's a little back underneath Superior and the boundary between Superior and the earlier accreted blocks. Is basically where the MCR is.
Yeah.
So it's taking advantage of that surface to fail between Superior and accreted blocks. anyway, I'm just throwing ideas out here.
Yeah, no,
trying to figure out, you know, what this might be.
and that's exactly what I'm hoping to do, right? Trigger discussion, get people thinking about this, and help me solve problems that have been bugging me for years.
Yeah, no, great question, Phil. You stole my question, I think. We have a little bit of background noise. Somebody does have their hand raised. I actually tried to figure out where the background noise was coming from, but anyway, Jim, if you want to go ahead.
Oh, I'm muted. Can you hear me?
Yep, you're unmuted now. Go ahead.
Good talk, Pete. I just wanted to, by the way, I completely agree that the single plume model just doesn't hold water really anymore for a 30 million year magmatic event. But there's some, the work that Nick Swanson-Heisel's doing is kind of, the idea that Laurentio was clipping along at a credible rate. It covered almost something like 40 degrees of latitude throughout the rift. And so he's been suggesting that, yeah, there could be far field effects, during that time, collision with other, subcontinents, but also that if we had this super plume kind of overheated mantle, the rift could have been passing over, plumes at different times, an early plume and then a later hotspot that it trips over at some other, later time in the rift. So that's kind of an intriguing idea too, that it's actually a combination of things that give rise to this really long-standing magmatism. What do you think of that, Pete?
Yeah, I think anything's possible, right? I don't know how we test that, because the geochemistry doesn't lend me to believing there are multiple plumes. There's nothing necessarily hugely distinctive, I think, in the geochemistry over different times. We're seeing the same signatures again and again. So maybe, that we're looking at maybe the early ultramafic stuff is one, and then we've moved over something else. I think that's possible. The other idea Nick tried to convince me of at some point, which I never really understood, was that the whole sort of lithosphere becomes detached from the mantle and spins freely, and that could explain. I struggle to figure out how that would actually work, but
yeah.
I think that's possible. Again, I don't know how we test it, and that's where I sort of struggle with the limits of the geochemical methods we have now. If we want to argue that each phase represents multiple plumes,
yeah,
how we recognize that.
The thing about that too is that the lithosphere has been damaged. It doesn't behave the same way every time it encounters a plume, because it experienced a previous plume and developed a plumbing system, and it basically isolated the crust from the conduits and all that sort of stuff, which we see in the rift. That like the contamination signature goes away from main stage on. You only see contamination in the early stages of magmatism. So it's when that magma is making its way through this rather pristine crust that you really see interactions and development of the underplate and all that kind of stuff. So it's an intriguing idea, and I don't think you can, the idea that Laurentia is moving, that's pretty solid. That's a solid piece of data that I think is hard to refute. So you have to kind of take that as something of a given, and then figure out what the other continents are doing and so on.
That's where I struggle a bit, right? Because if the other continents are static, then Laurentia should almost be playing pinball through this system, right? And we know there are other plume events recorded in different places. And when some of those earlier, the Umkondo ages and the Kalahari and all that sort of stuff, people have told me fairly convincingly that those are probably not the same plume event that we're seeing anywhere else, right? There are reasons they don't are the same thing. So I think the idea that there's something very unusual with the Earth's mantle at 1100 million years, whether it's what do they call them? Mantle overturn major orogeny event or a super plume.
Wells and
yeah. Is that what we're seeing, and is that why we're seeing this? Yeah, I could totally believe that.
Yeah.
Could I just comment that all of the other places with this 1100 magmatism at that time do potentially group together, as a separate plume. So it would seem that there is at least, there's multiple things going on at the same time. A center associated with the India, Congo, Amazonia, Kalahari components, of blocks, and then the separate one with Laurentia potentially, including also the southwestern Laurentia event. Anyway, yeah. So it's certainly an active time, and there are other active times where you seem to have multiple plumes of the same age going on, like 1385 and like 1880 and so on.
And I think that the stuff in the Southwest is interesting, right? Because that's how you tie the Southwest US stuff into the Midcontinent Rift is a challenge in many ways, I think.
Well, what we did with the Bright-et-al thing of having a plume come up and then deflected by the lithosphere, sort of deep portion of the lithosphere, and sliding a couple ways is maybe in vogue a bit these days for doing that for other plume events, and it would be neat to get some geophysical tests of that in some areas.
Wonder if I can chime in for a minute.
Go ahead, Dave.
I have two questions / comments. It would be good to get some feedback on. The first is inconsistencies that I see in the isotope work. And probably the best example is the difference between the Thunder intrusion and the Schillebeer intrusion. They both have very similar chemistry, but Schillebeer has an epsilon neodymium of -6, and Thunder's at +1. 0 to +1. So on the one hand, we're using negative values for neodymium to say that it's crustally contaminated, but there are times where for example, thorium niobium, is it's about +2 or less than 0.2. So it's hard to reconcile geochemistry to some of the isotope evidence. Does that mean anything to you, Pete?
I think each of the intrusions can have a very unique contamination history, right? So if you look at even the Osler volcanics, the basal Osler are pretty much primitive and uncontaminated. And as you move up the Osler sequence, they become increasingly contaminated. And we think the Osler represents maybe 1 or 2 million years of magmatism. So there's something happening in the feeder chamber for that over time, which is modifying the chemistry. It's not an emplacement because these are flows. I think if we look even at the Nipigon sills, right, there are different levels of neodymium contamination. So I think the contamination story is complex, and I'm not sure we fully understand it yet. The tie-in with geochemistry and isotopes, so the whole rock geochemistry and the isotopes, is a little trickier to piece together. Jeff's been playing with this, and I know you've been playing with it as well, trying to make those stories. And I think what we struggle with is we don't necessarily have really good ideas of what potential isotopic contaminants are and what their geochemical signatures might be. And that limits our debate. So, are we assimilating gunflint, or are we assimilating something at the lower crust? So, 2 or 3 kilometers down, or are we doing it at 20, 30 kilometers down? And I think we're not being able to resolve those differences, make it challenging to discuss or to know for sure what the geochemistry and the isotope data is telling us together.
Okay, so I guess that means that if you can't reconcile isotopes to geochemistry, but the geochemical relationships between many of the units with different isotopic signatures mean something. For instance, if 2 intrusions have the same geochemical signature with different isotopes, then, step back and maybe what I'm going to do is I'm just going to summarize is I stopped using the isotopic evidence, and I'm just using geochemistry to correlate units. And it works really well. For example, you mentioned the basal Osler volcanic group. That lower unit is geochemically similar to all of those ultramafic intrusions, which you probably knew. But geochemically, man, they're the same. And even units 1 and 2 over at Mamain's Point, very similar characteristics. So in my mind, with the way I think of this is basal Mamain's, basal Osler, and the ultramafic intrusions like Quito and the rest is the same. It's the same event. And then if you take that approach, then your age dates of 1117, I think, for Quito and 1110, etc., means that you have one event that lasts a long time, and it's coming from one source, one mantle source. Regardless of contamination.
Yeah, I think there's probably some, well, it depends how you want to think about this. If you want to accept Nick Swanson-Heisel's idea that it's moved 1,000 kilometers in the lifespan of the rift, it's hard to imagine it's tapping the same source all the time, right? So
Unless the plume head's riding with it.
Unless the plume head's riding with it. And I've never been hugely comfortable with that idea. I suppose I don't know, do we know examples where that's happening today, that plume heads are detached? Is that what's going on in the camera? I don't know. Maybe, yeah. I guess nothing's impossible. 1 billion years ago, we can wave our arms as much as we want. I think, there is very complex magmatic and contamination history. So yeah, the Mamain's Point and the Osler basal volcanics look very similar geochemically, but a few million years apart in age, right? So that does suggest they've tapped the same source initially, and I don't know if I have a problem with that, particularly there being a deep ultimate source to these things, which gets tapped and then undergoes different contamination, fractionation histories as it's erupted in place. Yeah.
Well, thanks. One of my thoughts, similar to Dave Goods, is, and I talked actually to Declan DePaolo about this issue, is that a lot of people blindly use epsilon neodymium to indicate crystal contamination when there's lots of rocks that are erupting and evolving to surface that have relatively flat repatterns, and therefore their projections are very much shallower through age towards more negative values. But there's many rock sequences that will retain fairly positive values throughout much of their existence. So we have to be careful, use multiple isotopes, or and test things in other ways. So we should definitely be careful about using just epsilon neodymium on its own. Anyway, I think we ran out of questions here in the chat, so I just invite people. I'm going to stop recording now, Pete, and people can just chime in and discuss things and hang out.